predicting throughput loss in process with no buffer. A motivating example for this topic will be a trauma center in a hospital. This is the unit in a hospital that receives patients in very serious conditions, patients who are in danger of dying and must receive help immediately, or they could pass away. A trauma center will, because of this, have no buffer. There's no waiting line for a trauma center. If all servers are occupied, then what is happening often in well-organized medical systems is that the hospital will be put on a diversion status, which basically means that it cannot receive patients, and then the ambulance, whether it's a car or a helicopter, will know that it shouldn't deliver patients to this hospital and has to choose another hospital, which is maybe further away, but at least it has available space for the patient that is in the ambulance. So here you see a picture of right, a kind of process flow diagram that shows what is happening here. There is 3 servers, the demand arrives here, and notice there is no buffer. The only thing that we could put here a diamond that would indicate, is the trauma center full? No, then the patient goes here. Yes, then the patient is diverted, and from the perspective of this trauma center, the throughput is lost, right? So the flow rate will be only the demand that is served, not all the demand in this case. So the questions we might ask is, what's the percentage of time patients will be turned away? So this is a probability which we'll call PM. M is for the number of servers, right? So there's a certain probability that at given time the patients will be turned away. And also, what's the percentage of patients that will be turned away? It also actually is the same probability PM. How many patients will be treated per day? This is the question about the flow rate. So remember, this is part of the demand that actually goes through the trauma center. And what's the percentage of patients that will be diverted per day? This is the percentage of demand that is lost, right? What's the throughput loss? This is not a percentage, it's number of patients per day, let's say, that will be diverted. So what are the calculations that we need to do? Well, we need to find the probability PM of probability that all servers are busy. And that probability will depend on the number of servers, M, the inter-arrival time A, and the service time P. And the calculations that we will do are, first we will calculate the implied utilization as demand divided by capacity, which is 1 over A, right? One customer arrives every A time units, and we can serve, the capacity is M, because we have M servers. We can serve M customers every P time units. P is the average service time, so this can be simplified to P divided by M times A. And then we will calculate this parameter R. The parameter doesn't have a special meaning, it's just the rate of service time to inter-arrival time, but it's necessary for the Erlang loss formula, which is the formula that calculates probability of the system, all servers being busy. And the formula is quite complex. We will not calculate it directly. We will use Excel or another software to compute this formula. Once we have the probability, we can calculate the flow rate as the percentage of demand that is not lost, 1 minus PM, and the throughput lost as percentage of demand that is lost, which is PM, right? And of course, demand is 1 over A, so we can use this calculation. Some comments. Exponential inter-arrival times are assumed, so of course coefficient of variation for arrivals or inter-arrival times is 1. And no assumption is made on service time distribution or coefficient of variation of the processing time or service time. And since demand can be turned away, we no longer need to assume that utilization is less than 1. We can work with utilization 100% or implied utilization 100% or even higher than 100%. So it is different than what we had in the case of waiting line models, where it was necessary to have utilization and implied utilization less than 1. In this case, implied utilization can be higher than 1 because we are anyway assuming some demand will be lost. Let's consider an example with numbers for the trauma center. So suppose we have 3 bays, so M is equal to 3. Suppose on average one patient arrives every 3 hours, right? So A is 3 hours. On average, service takes 2 hours, so P, processing time, on average is 2 hours. And also, let's assume one day is 24 hours, so we operate 24 hours, right, continuously. So let's calculate things that are interesting. First of all, what's the demand? Well, demand will, of course, be 1 divided by A, and it will be, right, 1 per 3 hours. So in hours, it will be 0.3333 patients per hour, right? But we can also convert it to patients per day. If I multiply this by 24, I'm going to get 8 patients per day. What about capacity? Capacity will be M divided by P, right? I can serve, because I have 3 servers, I can serve, or M servers, I can take M patients per P time units, P being the average service time. So this is going to be 3 over 2, that's 1.5 patients per hour, right? And again, if I convert this to per day, multiplying by 24 will give me 36 patients per day. I hope you notice immediately we have plenty of capacity. We can serve 36 patients a day, and we expect on average 8 patients a day, right? So let's do the calculations, right? Obviously, utilization U, right, will be, let's use symbol U, equals demand over capacity, right? And so that is 0.2222 or 22.22%. Very low utilization. R, as we said, is U times M. So it is, we can also express it as P over A, right? This is equivalent, if you, whichever you like, whichever you will use, it will be 0.6667, right? So this is the parameter R, and now we're ready to calculate PM. Remember, PM is calculated using the formula, the Erlang loss formula, as a function of R that I showed you earlier. So there is this function, right? I'm not going to do the calculations. Oops. I'm going to use Excel. So I prepared a little spreadsheet here that has all the formulas. So I entered 3 servers, 2 hours. So this is going to be for me in hours. And this is going to be in hours also, the average time between arrivals and average service time. The demand is calculated in patients per hour, right? And the capacity is also in patients per hour. And in this case, utilization is, of course, 22, or you could say in percentage terms, 22.22%. This is R as we calculated it. And there is the calculation here. This calculation actually uses some formulas that are step-by-step calculated here for a maximum of 20 servers that is in the spreadsheet. And so if you calculate the PM using Erlang loss formula, you get almost 55%. So let's go back to our writing, right? So using Erlang loss formula, we get 2.55%. So notice it's actually amazing because we have only 22.22% utilization. We have way more capacity than the demand. Yet 2.55% will be of demand will be lost, right? So in fact, our flow rate, right, which we can calculate as percentage of demand, right, that we will serve, which will be, right, demand times PM, 1 minus PM, right? This is the percentage of demand that we will serve, will be, right, 8 times, let's call it per day, 8 times 100% minus 2.55, which will give us 97.45%, right? So that is going to be 7.796 patients per day. And the throughput loss will be, right, also this demand times just a probability PM, right? So this is going to be 8 times 2.55%. And if you do the calculation, that's 0.204 patients per day, right? It may seem like not a lot, right? It's just a fraction of a patient per day. Or if you like, for 5 days, we are going on average to divert one patient. Every 5 days, one patient, right? And of course, note that these two, flow rate and throughput loss, they will add up to the total demand, right? Demand equals flow rate plus throughput loss, right? So these two numbers together, they are adding up to 8 patients per day. So of course, I can see the same calculations in this little spreadsheet that I have here, except that this is flow rate per hour, right? So if I want to convert it per day, I would have to multiply this by 24 to get it per day. And you see the flow rate is 7.79796. And here the lost demand is 0.2 roughly patients per day. So let's consider a variation of the question. We have, suppose another trauma center operating nearby is closed. And because of this, the demand that we experience increases from 8 patients per day to 18 patients, right? So now demand equals 18 patients per day, right? And so what does that do? Well, if now we have if you like, we can express this as 0.75 patients dividing by 24, right? Patients per hour. And so that means, right, A is equal to 1 over demand, and that will be 1.333 hours, right? So every, let's make this shorter, hours. Every 1.333 hours, we will have one patient arriving, right? Capacity is still as before, so we can actually use the Excel file to evaluate what is going to happen. Instead of A being every 3 hours we have a patient, we have now one patient every 1.333 hours. And what we're going to observe is now the probability we're full is not 2.5%, it's 13.4%, right? So it's much higher probability. Now, percentage of patients that we will divert from the 18, from the 18 patients a day, we will be diverting 2.4 patients every day. So the diversion status will be much higher. And this is despite the fact that our utilization is still only 50%. So here is the summary of the calculations, right? And we see the utilization is 50% instead of 22%. And the effect is much higher probability of diversion and also much larger percentage of the now increased demand is going to be diverted every day. Notice that before we had 8 patients a day, now we have 18 patients a day. And so therefore the diversion of 2.42 patients per day is not only larger in absolute terms, but it's also larger in relative terms to the new demand. So some considerations that I want to point out is implied utilization of 22% or even 50% with an environment with very high fixed costs seems like a nightmare, right? A hospital, the trauma centers are very expensive equipment that cost millions of dollars, but it is necessary to accommodate variability right? So we have to have this very low utilization. When there is no buffer, a lot of extra capacity is needed to accommodate variability, or we're going to have a very high loss of throughput. And you can imagine that the diversion might actually, when it happens frequently, might risk lives of a lot of patients. So treat utilization here with care, because the goal of the trauma center is not to maximize utilization, all right, to minimize costs. The main goal is to save lives, and therefore utilization should be treated as the major objective.